Alright, so here's our last problem on this. So again, we're trying to find the IMFs. We start with the Lewis structure. So NH3, we find its budget. Turns out it's 8, 5 from N, 3 from the H's. CH3F, you get 4 from carbon, 3 from the hydrogen, 7 from the fluorine, for a total of 14. Alright, so NH3, its central atom is N. Put an H on each one. And then we got to make sure they all have 8, except hydrogen, which is fine with 2. So in this case, I'm just adding dots to N. H is good. My budget was 8, 2, 4, 6, 8. This is good. It checks out. CH3F, I'm going to say, okay, which is my central atom? Typically, if carbon is your choice, you start with that. It can form the most bonds. We're just going to bond one of each of these to this. So CH3 and then F. Make sure they all have 8. Carbon's good with its 4 bonds. H is good. F just needs some dots. We needed to check our budget, 2, 4, 6, 8, 10, 12, 14. It checks out. So Lewis structures are both good. All right, let's find the shapes. So again, we count groups. NH3 has 1, 2, 3, 4 groups. So its electron geometry is tetrahedral, so it's going to make 4 groups as far apart from each other as possible. And so I'll put some H's on these ones, and then this one's just going to be a lone pair. So it's a trigonal pyramid molecular geometry. This other one also has 4 groups, so I'm going to also make a tetrahedral basic shape, but this one's going to have atoms on all 4. Now, it doesn't really matter which one I put the F on. I'll just put the F up top for now, but we could put them wherever we like. Alright, now we want to figure out if the molecules are polar or not. So we need to look up our electronegativities. N has an electronegativity of 3.04 as we look it up. Hydrogen is 2.20. Difference is 0.84. Again, 0.4 or more and the bond is polar, meaning the electrons shift towards one atom more than the other. They always shift towards the one with higher electronegativity, so nitrogen will be somewhat negative. Each of these hydrogens will be somewhat positive. And then we draw arrows from the positive towards the negative. These are all moving up the pyramid, so the overall polarity is upward. So this is in fact a polar molecule. And the other way we could tell this is we could divide this here, all the negatives above the line, all the positives below the line. All right, next one we're going to look at is CH. So C is 2.20, 2.55. H is 2.20. So the difference is only 0.35. Not enough of a difference. So all these bonds are non-polar. And I'm going to write NP over them just so I remember. And don't draw any charges along those bonds because they're not polar enough for charges to form. I'll look at the CF bond on the other hand. F is 3.98. Carbon was 2.55. That's a severe difference, enough to make fluorine negative and carbon positive. So there's a pole, an arrow moving up towards fluorine. Now, because that's the only arrow, that means there's definitely a general direction. It's up. I can definitely isolate the negatives and positives. So this is also a polar molecule. So they're both polar. So the question is, which one is probably with stronger IMFs? So the tiebreaker we can look at first is there hydrogen bonding? So remember, hydrogen bonding occurs anytime you have an H to F, H to O, or H to N bond in your molecule. It creates a scenario where you have more extreme polarity. So this one here has an H to N bond. It has actually several of them. So this exhibits hydrogen bonding, which is again a stronger version of IMFs. This one does not. It has H and F, but they're not connected to each other. So this one just has your standard garden variety dipole-dipole forces. So if we had to guess, we'd probably say that NH3 has stronger IMFs. Now, the molar mass can also play a role here, but just generally speaking, we would say this is probably stronger. So which one's more likely to be the solid? It's the one that's going to hold together more effectively. So NH3 is more likely to stick together. You're more likely to find NH3 as a solid. At room temperature, they're both gases, but in this case, if we had to cool them down, we could make this one a solid more easily because it has stronger IMFs from its hydrogen bonding. So again, that's the process you have to go through on these types of problems. Try them out, practice, and that's it. So until next time, I am Derek Genova. Have a delightful day.